A telescope sitting 1 million miles from Earth is sending back data that does not fit. Galaxies too massive to exist. A planet exhaling a gas only living things produce on Earth. Stars measured to be older than the universe itself. The James Webb Space Telescope was built to answer our biggest questions. Instead, it keeps generating new ones, and some of them may shatter everything science thought it had confirmed. If this journey sounds like one worth taking, like and subscribe. Now brace yourself. We begin. The James Webb Space Telescope speaks a different language than every telescope before it. Every previous instrument, including the Hubble, read the universe primarily through visible light, the same narrow band of color the human eye detects. That works reasonably well for nearby stars and relatively close galaxies. But the universe has a fundamental problem with visible light. Dust blocks it. Distance stretches it. By the time ancient light travels billions of years to reach us, the universe has expanded so much that those original wavelengths have been pulled into infrared, a frequency invisible to human eyes and to most instruments ever built. JWST was engineered specifically to receive that stretched ancient signal. Its primary mirror spans 21 feet across, nearly 3 times the width of Hubble's. Raw size is only part of it. The mirror consists of 18 hexagonal segments, coated in a layer of gold just a few atoms thick. Gold, specifically, because it reflects infrared light with extraordinary efficiency. Each segment was individually tuned after launch to align within a fraction of the width of a human hair. The precision required was so extreme that engineers compared it to making adjustments from over 1 million miles away, because that is exactly what they did. The telescope was positioned at the second Lagrange point, a gravitational balance location sitting 1 million miles from Earth in the direction away from the Sun. JWST orbits the Sun in sync with Earth from that position, always keeping our planet between itself and solar heat. Infrared detection requires the instrument itself to be cold, far colder than anything in the natural environment near Earth. A sun shield the size of a tennis court keeps the telescope chilled to around -440 degrees Fahrenheit. Without that extreme cold, the telescope's own heat signature would overwhelm the faint infrared signals it hunts. That hunting began in earnest when calibration completed in mid-2022. The calibration phase itself took 6 months, a painstaking process of aligning 18 mirrors in the cold darkness of space. When the first test images came back, engineers circulated them internally before any public release. Several described the experience of seeing those early frames as deeply unsettling. The resolution exceeded every benchmark. The depth pushed past every prediction. The universe, it turned out, had more to show than anyone had accounted for. And almost immediately, something felt wrong. The data flowing back did not match expectations. Models built over decades had prepared scientists for what JWST should find. The telescope was expected to confirm existing timelines, extend human sight a little further, sharpen the picture at the edges of the known universe. Researchers were ready for incremental discovery. JWST delivered something else entirely. The infrared window opened and revealed a universe that looked fundamentally different from the one cosmology had carefully described. Structures appeared where structures should not have had time to form. Distances stretched further than predictions allowed, and at certain wavelengths, the data contained readings that no instrument calibration issue could fully explain. Scientists ran the checks. They tested for equipment error, atmospheric interference, transmission artifacts. The anomalies held. Here is the key distinction that set JWST apart from every instrument before it. Previous telescopes showed us light from the early universe. JWST showed us structure. The difference between those two things is the difference between seeing a glow on the horizon and seeing the city that produces it. Humanity suddenly had an overhead map, and the city was laid out completely differently than the blueprints said it should be. Every discovery in the chapters ahead traces back to that infrared window. The tool designed to confirm our model of creation began dismantling it instead, one image at a time. What the first deep field photograph revealed would stop the scientific community cold. The image arrived on July 11, 2022, and the room at NASA went silent. The first official deep field photograph released from JWST covered a patch of sky roughly the size of a grain of sand held at arm's length. A nothing-sized slice of the universe, chosen almost at random, and packed inside that grain of sand was a cosmos teeming beyond comprehension. Thousands of galaxies filled the frame. Every smear of color, every curved arc, every faint pinprick of light was an entire galaxy containing hundreds of billions of stars each. Some appeared as crisp spirals. Others had been warped by gravity into glowing crescents and rings. The light from the most distant objects had been traveling for over 13 billion years before hitting the telescope's mirror. But the silence in that room carried more than wonder. It carried unease. Astronomers scanning the image noticed something almost immediately. The galaxies near the edges of the frame, the oldest ones, the furthest ones, the ones that should have existed in the raw, unsettled chaos of the early universe, looked too developed, too structured, too complete. Standard cosmology operates on a well-tested timeline. After the Big Bang, the universe spent hundreds of millions of years as a dark, formless sea of gas and energy. Gravity slowly pulled material together. Clouds collapsed. The first stars ignited. Eventually, over vast stretches of time, those stars grouped into the first primitive galaxies. Small, chaotic, irregular. Mature galaxies took billions of years more to build. That timeline predicted what JWST would see at its maximum depth. Primitive structure, early chaos, the universe in its rough first draft. JWST sent back a finished manuscript. The galaxies sitting at distances that placed them in the universe's first billion years carried the hallmarks of maturity, defined shapes, enormous mass concentrations, stars distributed in organized patterns. One team, measuring a cluster of galaxies in the image, described it as finding a fully constructed skyscraper at a location where, according to every known rule, only bare ground should exist. Researchers flagged the anomalies. Then came the follow-up images. Each new deep field confirmed what the first suggested. The further JWST looked, the more consistently the universe defied expectation. The chaos that cosmology predicted in the early universe was there, but it was surrounded and in some cases replaced by order, by structure, by objects that should have required far more time to assemble. A small group of scientists quietly began using a phrase that larger institutions were not yet ready to publish: the early universe problem. The phrase points at a very specific crack in our understanding. If galaxies were fully formed that early, then either something was dramatically accelerating the pace of cosmic construction, or the timeline itself was wrong, or something preceded the Big Bang and seeded the universe with structure we never accounted for. Each of those possibilities tears apart a different section of the standard model. The images kept arriving, each one a little older, a little deeper, a little more unsettling. And tucked inside the most recent deep fields, something small and red kept appearing in clusters, in places it had no business being. Those small red shapes would become one of the most debated anomalies in modern astronomy. A galaxy takes time. That is one of the most foundational assumptions in cosmology, and for decades it held up under every test thrown at it. You need gas, you need gravity, you need hundreds of millions, often billions, of years for that gas to condense, for stars to ignite, for those stars to die and enrich the surrounding space with heavier elements, for new generations to form from that enriched material. Building a galaxy is slow. It is cumulative. The universe does not rush it. JWST found galaxies that rushed it anyway. Several of the most significant detections from the telescope's early observation runs revealed massive galaxies sitting at distances that placed their formation within 300 to 500 million years of the Big Bang. In cosmic terms, that is almost nothing. The universe is approximately 13.8 billion years old. 300 million years in is less than 3% of its current age. Finding a fully formed, massive galaxy that far back is roughly equivalent to discovering a fully grown adult human at the moment of biological conception. The numbers involved are staggering. Some of these early galaxies appear to contain stellar mass comparable to the Milky Way, our own galaxy, which has had over 10 billion years to assemble itself. Several candidates exceed that mass. One system identified in data from the first year of observations appeared to contain roughly 10 billion times the mass of our Sun in stars alone, and it existed when the universe was younger than 300 million years old. The physics of galaxy formation simply does not account for that speed. A team of astrophysicists publishing in a major journal in 2023 described the discovery bluntly. These objects should not exist within the standard model of cosmic evolution. The standard model, called lambda CDM, has been the backbone of modern astronomy for decades. It predicts how structure grows over time. It maps how dark matter halos gradually accumulate mass and pull ordinary matter into them. It describes galaxy formation as a slow, hierarchical process. These galaxies did not follow the process. Some researchers proposed that star formation in the early universe may have been dramatically more efficient than anything observed in the modern universe, converting raw gas into stars at a rate far exceeding anything seen today. If true, that alone would demand a significant revision to star formation models. Others went further. They suggested that if these galaxies truly exist at those distances and with those masses, then something about the age of the universe may itself need re-examining, the very foundation of the timeline. Here is what makes this genuinely unsettling. These are not fringe detections. Dozens of candidate galaxies fitting this description have now been catalogued. Multiple research groups across multiple continents have confirmed the core observations independently. The data has been reviewed, questioned, and reviewed again. The galaxies are real. The distances appear accurate. The masses, while carrying some uncertainty, remain far too high to dismiss. And sitting at the center of several of these ancient, impossible galaxies, something even harder to explain was already burning. Something that should have needed billions of years to grow, but clearly did not wait. Lambda CDM is the name scientists gave to the best explanation humanity has ever produced for how the universe works. The letters stand for lambda, the cosmological constant representing dark energy, and cold dark matter. Together, they form a mathematical framework describing how the universe evolved from the first moments after the Big Bang, all the way to the present day. It correctly predicted the large-scale structure of the universe, the temperature variations in the cosmic microwave background, and how galaxy clusters distribute across cosmic space. For decades, it passed every observational test with remarkable precision. JWST is applying pressure the framework was never tested against. To understand why, consider what lambda CDM specifically predicts about the early universe. In its framework, dark matter halos form first, invisible gravitational scaffolding that slowly accumulates over time. Ordinary matter falls into those halos, cools, and forms stars. Those first stars are massive, short-lived, and violently destructive. They enrich the surrounding gas. The next generation forms from slightly more complex material. Over hundreds of millions of years, this process stacks and layers until something recognizable as a galaxy begins to emerge. The process is hierarchical. Small things form first, Larger things form from the merging and accumulation of smaller things. A fully massive galaxy appearing within the first 300 million years skips most of the queue entirely, and the contradictions extend beyond mass alone. Several of the early JWST galaxies show signs of mature stellar populations, meaning stars that formed, lived full lives, and died before the galaxy was even fully assembled in the standard timeline. The chemical complexity visible in the light from these ancient systems reflects multiple generations of stellar evolution. Multiple generations require time the early universe had not yet provided. Some researchers have proposed modifications to lambda CDM rather than outright replacement. Perhaps dark matter behaves differently in the early epochs. Perhaps early star formation was fueled by a different mechanism, one that temporarily bypassed the usual constraints. These are legitimate scientific possibilities being actively tested. But others are raising a harder question. What if the framework itself needs replacing? Alternative cosmological models have existed on the margins of physics for years. Some propose that the universe did not begin in a singular explosive event, but instead emerged from a prior contracting phase, a bounce. Others suggest that the laws of physics themselves were different in the early universe, allowing structure to form at speeds current equations forbid. These alternatives were largely theoretical exercises before JWST. Data was not available to test them meaningfully. Now the data is arriving fast. Cosmologists in multiple institutions have quietly begun reassessing fundamental assumptions that the field has treated as settled for a generation. The conversations happening in seminar rooms and on preprint servers are more urgent than anything filtering into mainstream science coverage. The galaxies are pushing the framework to its edge, and the further JWST reaches, the more pressure builds. But the massive galaxies were just the opening act. Because lurking in those deep field images, clustered in the corners like something the universe was trying to conceal, were objects stranger than any fully formed galaxy. Small, dense, red, and completely unexplained. When researchers began sorting through the first full year of JWST data, a pattern emerged that nobody had predicted. Scattered across the deep field images, appearing in concentrations that grew denser the further back the telescope looked, were compact objects, emitting light heavily skewed toward red wavelengths. They were small on the detector, but small at cosmic distances is a relative term. These objects, if their distance measurements are accurate, are genuinely compact in a way that standard galaxy formation does not allow. Scientists named them little red dots. The informal name stuck precisely because no formal classification fits them well enough to replace it. They appear throughout the early universe, concentrating in the period between about 600 million and 1.5 billion years after the Big Bang. Their number is the first problem. There are far more of them than models predicted. Early estimates place the excess at roughly 10 times the expected count. Subsequent analyses pushed that number higher. In some wavelength ranges, the abundance of these objects exceeds theoretical predictions by a factor closer to 100. 100 times more than should exist. Their nature is the second problem. The red color suggests one of two things, or possibly both simultaneously. Heavy dust absorption reddens light as dense clouds of particles scatter blue wavelengths and let red ones through, giving a galaxy a deep crimson tint. Alternatively, a very active black hole at the center of a compact galaxy can produce a specific spectrum of light as it consumes surrounding material at extreme rates. Both explanations carry their own crisis. If the little red dots are dust-shrouded galaxies, they contain an enormous amount of material formed incredibly early, feeding the same problem of galaxies being too massive too soon. If they are compact objects powered by extremely active black holes, then those black holes grew to enormous size within the first billion years of the universe. A black hole does not grow fast. It grows slowly, consuming material at rates limited by the very radiation its own feeding process generates. The physics of black hole growth sets a firm speed limit. Something appears to have broken that speed limit. A team analyzing a subset of little red dots in 2023 found spectroscopic signatures suggesting some of these objects might be both things at once. Young, compact galaxies hosting rapidly growing central black holes wrapped in thick dust, all compressed into a region smaller than most modern galaxies by a factor of 10. The density implied by those measurements is difficult to reconcile with any standard model of structure formation. What makes these objects genuinely disturbing to astronomers is their prevalence. They are everywhere in the early universe. If they represent a phase of galaxy or black hole evolution, it must have been a dominant phase, one that affected almost every structure forming at that time, and yet no equivalent population exists in the modern universe. They appear and then somehow vanish from the cosmic record. Where did they go? What did they become? The data does not say, and buried in the spectroscopic readings from the brightest little red dots, instruments began picking up something that connected these ancient objects to an even more pressing question. How do you build a black hole the size of 1 billion suns before the universe is even 1 billion years old? A black hole starts small. That is the rule. The most common origin story begins with a massive star, something at least 20 to 30 times the mass of our Sun, collapsing under its own gravity at the end of its life. The resulting black hole might contain a few times the Sun's mass. From there, it grows by consuming nearby gas and dust, occasionally merging with other black holes. The process accumulates mass over enormous timescales. Most supermassive black holes, the kind sitting at the centers of large galaxies and containing millions or billions of solar masses, are thought to have grown over billions of years of continuous feeding. JWST has found them fully grown in the infant universe. The telescope's infrared sensitivity allows it to detect the characteristic glow produced by material falling into a black hole. This structure, called a quasar, forms when the surrounding disk of infalling material heats to extreme temperatures and radiates energy across multiple wavelengths. By analyzing the redshift of that light, astronomers can calculate both the distance to the quasar and the approximate mass of the black hole powering it. Several quasars detected by JWST within the first billion years of the universe contain black holes with masses reaching into the hundreds of millions to low billions of solar masses. One candidate, confirmed by spectroscopic follow-up, sits at a distance placing it less than 600 million years after the Big Bang. Its central black hole carries an estimated mass of several 100 million times our Sun. Physicists call the theoretical growth ceiling the Eddington limit. It defines the maximum rate at which a black hole can consume mass before the radiation it produces pushes surrounding material away, throttling its own feeding. Growing a black hole of several 100 million solar masses from a stellar remnant of a few solar masses, even at the Eddington limit continuously, requires hundreds of millions of years at the absolute minimum. The universe at 600 million years old had barely that much total time to produce the first generation of stars that could collapse into black holes in the first place. Several explanations have been proposed. Some models suggest that the very first stars, called Population 3 stars, and never yet directly observed, were enormous by modern standards, hundreds of times the mass of our Sun. When these giants collapsed, they may have produced initial black holes with far more starting mass than typical stellar remnants, giving them a significant head start. Others propose that these early black holes fed at super Eddington rates, breaking the theoretical speed limit entirely through mechanisms that physics has not yet confirmed but cannot definitively rule out. A third possibility, discussed in several high-profile papers, involves the direct collapse of massive gas clouds, bypassing the stellar phase entirely and creating a black hole of enormous size in a single, catastrophic event. The conditions for direct collapse would have existed only in the very early universe, which is consistent with the observation that nothing like these objects appears in the modern cosmos. Each explanation demands either unknown physics, unknown objects, or unknown processes. Every path forward rewrites something considered settled, and the black holes were feeding on something in a universe that was, by multiple separate measurements, expanding faster than its own origin story permitted. Physics has a number for the expansion rate of the universe. It is called the Hubble constant, named after the astronomer who first measured cosmic expansion in the 1920s. For decades, measuring this number precisely was considered one of the most important goals in cosmology. Get the Hubble constant right, and you have a fundamental parameter describing the entire history and future of the universe. Two independent methods of measuring it produced two different answers, and they refuse to agree. The first method looks back. Scientists analyze the cosmic microwave background, a faint glow left over from roughly 380,000 years after the Big Bang, representing the earliest light the universe ever produced. By modeling how the universe evolved from that ancient glowing state to its current form, physicists calculate what the expansion rate should be today. This method gives a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method examines the current universe directly. Astronomers measure distances to nearby galaxies using standard candles, objects whose true brightness is known, so their distance can be calculated from how bright they appear. These measurements consistently produce a Hubble constant closer to 73, 67 versus 73. The gap looks small. In cosmology, it is enormous. In a field where measurements are expected to agree within fractions of a percent, a discrepancy of nearly 10% represents a fundamental breakdown somewhere in the model. Before JWST, many scientists hoped the tension was a measurement error. The instruments making the direct measurements had known imperfections. Perhaps systematic errors in the calibration of standard candles were inflating the result. If JWST could sharpen those distance measurements with its superior optics, the two numbers would finally converge. They did not converge, they pulled further apart. JWST confirmed and in some cases strengthened the distance measurements, supporting the higher value. The telescope's precision removed sources of error that had been flagged as potential culprits. When those errors were eliminated, the Hubble constant stayed stubbornly high. The implication is stark. Either the early universe measurement is wrong, meaning the cosmic microwave background is not telling us what we think it is, or the current universe measurement is wrong. The possibility that cosmologists find most uncomfortable is that both measurements are correct and the standard model contains a gap that nobody has identified. A universe expanding faster than its own origin story predicts points towards something missing from the equations. Dark energy behaving differently across cosmic time. A new force acting on large scales. Unknown particles influencing expansion in ways current models do not account for. Or something stranger. Something that touches the very definition of what the universe is and how it began. One proposal gaining traction in theoretical physics involves early dark energy, a form of energy that existed only in the first moments after the Big Bang and briefly accelerated expansion before fading away. It could reconcile the two measurements. It also requires an entirely new component of the universe that has never been directly detected. The Hubble tension is no longer a measurement quirk awaiting correction. It is a crack running through the foundation of cosmological physics. And every data point JWST sends back applies more pressure to it. What nobody anticipated was data suggesting the universe's timeline might need to be rewritten from the very beginning. The Big Bang is the beginning of everything. That premise is what the entire framework of modern cosmology rests on. Approximately 13.8 billion years ago, all the energy, matter, space, and time that make up the observable universe exploded outward from an extraordinarily dense initial state. Everything before that moment, if before even means anything, sits outside the reach of physics. The equations break down at time zero. The question of what preceded the Big Bang is, by most definitions, not a scientific question. JWST is quietly forcing that definition to change. Several independent lines of evidence emerging from the telescope's data hint at a universe that carries marks of something that happened before its supposed origin point. These signals are indirect. They require interpretation. Researchers presenting them are careful with their language, but the hints are accumulating, and they are coming from completely separate areas of observation. The first line of evidence involves the clustering patterns of galaxies on the largest scales. When JWST maps the distribution of ancient galaxies, certain regularities appear in how they cluster, periodic patterns in their spacing that look to some theorists like acoustic echoes. Echoes of pressure waves that traveled through a dense medium, a medium that would have predated the conventional Big Bang. The second line involves anomalies in the cosmic microwave background that existing measurements captured but could not explain. When JWST's data on early galaxies is used to cross-reference those anomalies, some of them sharpen rather than blur. Patterns emerge that might reflect conditions from a prior phase of the universe rather than noise from this one. A theoretical framework called bouncing cosmology addresses this directly. In that model, the universe did not begin from nothing. Instead, a prior universe contracted under gravity to an extreme density, approaching, but not reaching, a true singularity, before quantum effects reversed the collapse and produced an explosive expansion that looks, from inside the resulting universe, exactly like a Big Bang. Structures from the prior universe could have imprinted themselves on the new one. This is speculative. It remains theoretical. But the researchers developing these models are mainstream physicists at respected institutions, and they are pointing to JWST data as the first observational window through which signatures of a bounce might actually be detectable. A separate class of models involves what cosmologists call eternal inflation. In those scenarios, the Big Bang that produced our universe was a local event inside a vastly larger structure that has been expanding and producing new universes continuously. Our entire 13.8 billion year history would be a single bubble in an ocean of other expanding regions. Both ideas carry an uncomfortable implication. The universe we live in may be a consequence rather than a beginning. Scientists are cautious about these interpretations for professional reasons as much as scientific ones. The data from JWST is extraordinary, but it is also early. Follow-up observations are being rigorously tested. What has shifted is the conversation itself. Questions that were considered outside the domain of testable science 2 years ago are now appearing in peer-reviewed journals. JWST has opened a door the field did not expect to open this decade, and through that door, something even more immediate was about to step forward. A signal from a single planet that touched the one question no instrument was ever expected to answer. The hunt for life beyond Earth has never been short of ambition. For decades, researchers pointed instruments at distant planets and asked a single question: is there anything there? The answer was always the same. The planet exists. It has a mass. It has an orbit. Beyond that, almost nothing. JWST changed the terms of the search entirely. When a planet passes in front of its host star, a small fraction of starlight filters through the planet's atmosphere before reaching the telescope. Different molecules absorb specific wavelengths of that light. By measuring which wavelengths are missing, astronomers can determine which molecules are present in the atmosphere. The technique is called transmission spectroscopy. Previous telescopes could perform it on the largest, closest exoplanets with limited precision. JWST performs it on smaller, more distant worlds with a sensitivity no previous instrument could approach. The first major confirmation came from a planet called WASP 39b, a gas giant roughly the size of Saturn, orbiting a star about 700 light-years from Earth. JWST's analysis of its atmosphere returned a clear, unambiguous detection of carbon dioxide. That might sound modest. Carbon dioxide is a simple molecule. It exists on Mars, Venus, and in every breath every animal on Earth exhales. The significance lives in the method, not the molecule. Carbon dioxide is a benchmark detection. Its molecular signature in starlight is sharp and distinct, making it an ideal test case for the precision of transmission spectroscopy. By confirming a clean carbon dioxide detection at 700 light-years, JWST demonstrated that it can read the atmospheric chemistry of distant planets with a clarity that opens an entirely new era of planetary science. Every molecule that living systems produce on Earth, including oxygen, methane, and nitrous oxide, now falls within the range of what JWST can potentially detect on distant worlds. The telescope was designed with a wavelength range that covers the fingerprints of those molecules specifically. That was not an accident. The engineers building JWST knew what question the scientific community would eventually want to ask. Water vapor, sulfur dioxide, and complex organic compounds have since been detected in planetary atmospheres at distances that would have been unthinkable from any previous observatory. Each detection refines the technique. Each refinement narrows the gap between simply knowing a planet exists and actually knowing what its atmosphere is doing. For the first time in human history, humanity possesses a tool capable of detecting the chemical signature of life on a planet orbiting another star. Detecting it does not mean confirming it. Chemistry can mimic biology in many contexts. But the capacity to detect is the first step in a process that could culminate in the most significant discovery in human history. JWST has not announced a confirmed biosignature from any exoplanet. That boundary has not been crossed. But the instrument now scanning those distant atmospheres is the first in history with a realistic chance of finding one. And in the data already collected, one signal arrived that the scientific community could not easily dismiss. From a world orbiting within what astronomers call the habitable zone, the range of distances where liquid water could exist on a planetary surface, JWST detected a gas that on Earth only living organisms produce in significant quantities. That detection sparked a debate that is still running. The planet sits 120 light-years from Earth. It orbits a red dwarf star in the constellation Leo. It is roughly 2.5 times the diameter of Earth, placing it in a category called a sub-Neptune, too large to be a rocky world like ours, but too small to be a gas giant like Jupiter. Astronomers classify K2 18b as a Haitian world candidate. Haitian is shorthand for a hypothesized class of planet combining hydrogen-dominated atmospheres with vast liquid water oceans covering their entire surface. If Haitian worlds exist as theorized, the ocean beneath a hydrogen-rich atmosphere could maintain stable liquid water across a wide range of distances from its star. K2 18b sits inside the habitable zone. JWST pointed at it and found something unexpected. Carbon dioxide and methane were detected in its atmosphere. Not shocking in isolation, since both can have geological as well as biological origins. But alongside those two molecules, the data showed a tentative signal for dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, microscopic photosynthetic organisms living in the ocean. When those organisms metabolize, they release this compound into the atmosphere. It is considered a biosignature on Earth because no known geological or chemical process produces it in significant quantities without biological assistance. The detection was announced in 2023 by a research team at the University of Cambridge. They were careful with their language. The word tentative appeared repeatedly. The signal sat at a confidence level that the scientific community requires to investigate further, not to declare discovery. More observation time was needed. What the team was equally careful to state, they could find no purely chemical or geological explanation that would produce dimethyl sulfide in the concentrations the data suggested. The scientific response divided along predictable lines. Some researchers pointed to the possibility of unknown photochemical reactions in hydrogen-rich atmospheres that might generate dimethyl sulfide without biology. This is a legitimate hypothesis. The atmospheres of Hycean worlds are unlike any atmosphere studied on Earth or anywhere else in the solar system, and their chemistry is not fully mapped. Others noted that while the unknown chemistry argument is valid, it is also, at this moment, entirely theoretical. No confirmed abiotic process for producing that molecule at those concentrations has been demonstrated. The biology explanation, by contrast, has a working example: the ocean underneath every researcher making that argument. The debate has sharpened rather than resolved since the initial announcement. Follow-up observations from JWST's second year targeted K2-18b with additional hours of instrument time, specifically aimed at improving signal quality. Results from those sessions were still being analyzed and refined as of the time this script was written. The confidence level on the dimethyl sulfide detection was under active review. What is settled? K2-18b exists. Its atmosphere contains carbon-bearing molecules, and at least one of those molecules is a compound strongly associated with life on Earth. Whether life produces it there, or whether a chemistry never before observed in any planetary atmosphere produces it through some unknown process, remains genuinely open. That honest uncertainty is itself significant. Humanity has never been in a position where the question was this close and this unresolved. And the harder part is that, no matter how many times scientists tried to explain the signal away, it would not go. A scientific anomaly becomes dangerous when it survives every attempt to kill it. The history of science is full of signals that looked extraordinary and turned out to be noise. Equipment error, atmospheric interference, mathematical mistakes, confirmation bias leading researchers to overweight data supporting a preferred conclusion. The scientific community knows all of these failure modes intimately. When a result carries any hint of being too exciting, the first instinct is attack. The K2-18b dimethyl sulfide signal has been attacked from every available angle. The instrument calibration was checked multiple times. JWST's spectrographs are among the most precisely characterized scientific instruments ever deployed. When researchers applied calibration corrections and reran the analysis pipeline, the signal held, reduced slightly in confidence under the most conservative corrections, but present. The data reduction method was scrutinized. Transmission spectroscopy involves subtracting the star's baseline spectrum from measurements taken during planetary transit. Different research groups applied different reduction algorithms to the same raw data. Most recovered the signal. A small number of approaches produced weaker results, which the original team acknowledged and discussed transparently. The atmospheric model was challenged. Different models of K2-18b's atmospheric composition were tested to see whether other combinations of molecules could produce a similar spectral signature, while excluding dimethyl sulfide. Some configurations reduced the need for dimethyl sulfide, but none eliminated it cleanly from the data. The molecule's spectral fingerprint is distinct enough that completely mimicking it with other compounds requires chemical combinations that themselves raise further questions. The abiotic chemistry argument received the most careful examination. Several teams modeled possible photochemical reactions in a hydrogen-rich atmosphere under radiation from a red dwarf star. Some generated trace amounts of dimethyl sulfide through purely chemical pathways. The quantities produced were orders of magnitude lower than what the K2-18b spectrum suggests. The gap between theoretically possible trace production and the implied atmospheric concentration remained wide. What makes the debate particularly difficult to close is that K2-18b represents a type of planet never before studied in this depth. The scientific community has no equivalent ground truth. Every model of its atmospheric chemistry, whether predicting biology or excluding it, is built on assumptions that cannot yet be verified by direct measurement. The planet is 120 light-years away. No probe is going there. JWST is the only tool capable of generating data from that distance. Researchers advocating caution make a valid point. Absence of a known abiotic explanation does not equal presence of life. Science requires positive evidence, not just the elimination of alternatives. Researchers pressing for the signal's significance make an equally valid point. The positive evidence is the signal itself, a compound with no demonstrated geological source, appearing in an atmosphere that exists over a potential ocean on a planet in the habitable zone of its star. Dismissing it requires invoking an explanation that has never been shown to exist. The deadlock is genuine. Both sides are operating with integrity. What neither side disputes: if the signal is confirmed with higher statistical confidence in ongoing observations, this generation of scientists will face a choice about what to conclude that no generation before them has ever had to make. And at the same time JWST was locked onto K2-18b, its instruments were finding water in places where water should have been destroyed long ago. Water is fragile. In the chemistry of planetary atmospheres, the water molecule, made of 2 hydrogen atoms bonded to 1 oxygen, breaks apart under sustained ultraviolet radiation. Given enough energy and enough time, those atoms drift away into space individually. Hot planets orbiting active stars should be stripped of their water relatively quickly on astronomical timescales. That is the expectation. That is what the models predict. JWST keeps finding water where it should not survive. Several detections stand out. The telescope has identified water vapor signatures in the upper atmospheres of planets orbiting at distances and temperatures that standard photochemistry designates as incompatible with stable water retention. In some cases, the host stars are highly active, flooding their planets with radiation at levels that should accelerate molecular breakdown far beyond any natural replenishment rate. One particularly striking case involves an ultra-hot Jupiter, a class of gas giant that orbits so close to its star that surface temperatures reach several thousand degrees Fahrenheit. These planets represent the extreme end of the exoplanet scale. The day side of such a world experiences temperatures sufficient to vaporize iron. For years, water was assumed to be absent from these environments. The energy input should destroy it faster than any process could produce it. JWST found water vapor in the atmosphere of one of these ultra-hot Jupiters during its first year of operation. The detection was clear. The research team offered a tentative explanation involving atmospheric circulation. On ultra-hot Jupiters, extreme temperature gradients between the permanent day side and the cooler night side drive ferocious winds circling the planet at speeds exceeding several thousand miles per hour. Material from the night side, where temperatures allow water to survive, is continuously swept around into the day side. The water vapor detected may represent this night side reservoir being briefly exposed to dayside conditions before breaking down and being replenished by fresh material circling the limb. That explanation is scientifically reasonable. It also demands that the circulation dynamics of these extreme worlds are far more complex and efficient than previous models assumed. Other water detections carry fewer convenient explanations. Trace water signals have appeared in spectra of planetary atmospheres where the orbital geometry and stellar activity do not permit the circulation argument to apply. In those cases, the water is present in locations where every current model says it should not be, and no alternative mechanism has yet been proposed with enough detail to be tested. The broader implication runs deeper than any individual detection. If water persists in environments that should destroy it, the universe may be far more hospitable to the conditions that liquid water enables than the current inventory of hostile worlds suggests. Every confirmed detection of water vapor in an unexpected location adds a data point to the case that water is rarer in our models than it is in reality. Life, as every organism on Earth demonstrates, depends on liquid water as a fundamental operating requirement. A universe that retains water more tenaciously than expected is a universe with more candidate locations for biochemistry than anyone previously calculated. What JWST was finding in planetary atmospheres was unsettling enough, but when the telescope turned its attention to something far older than any planet, it encountered an object that should have been physically impossible by any clock ever constructed. The universe is 13.8 billion years old. That number comes from multiple independent lines of evidence, including the cosmic microwave background, the expansion rate of galaxies, and the abundance of light elements produced in the first few minutes after the Big Bang. It is one of the most rigorously tested figures in all of science. A star called HD 14283 is approximately 14.4 billion years old. That is the measurement. The star is older than the universe it lives in. A tree cannot predate the forest. A building cannot predate the ground beneath it. A star cannot predate the universe from which it condensed. And yet, the measurement keeps surviving scrutiny. HD 14283 sits about 190 light-years from Earth, exceptionally close in galactic terms, close enough that astronomers can measure its properties in extraordinary detail. Its age estimate comes from stellar evolution models, the science of how stars burn through their fuel and how their internal structure changes over time. By examining a star's chemical composition, luminosity, color, and mass, astrophysicists can calculate how long it has been burning with significant precision. Multiple independent teams have analyzed this star over decades. The age estimates cluster around 14 billion years, with uncertainty ranges that can dip as low as 13.6 billion, just within the boundary of the universe's age, or reach up to 14.6 billion, well outside it. JWST has sharpened these measurements by providing better calibration data for the stellar models used to calculate stellar ages. The telescope's observations have not resolved the tension. They have refined the uncertainty ranges, and while refined estimates technically allow for solutions that place the star inside the universe's age, they also preserve solutions that place it outside. The resolution to this apparent paradox involves uncertainty stacking on both sides. The age of the universe carries its own measurement uncertainty. A universe expanding faster than the standard model predicts would also be slightly younger than the standard calculation suggests, widening the gap rather than closing it. Some cosmologists point to this overlap of uncertainties as the source of the conflict, a sign that at least one measurement needs refinement rather than a genuine physical impossibility. That is the conservative, scientifically safe position. Others note something more provocative. This star belongs to a population called metal-poor stars, ancient objects formed from the first generation of stellar material after the Big Bang, before successive generations of supernovae enriched the universe with heavier elements. Metal-poor stars are the closest living relatives of the very first stars ever formed. Finding one that approaches or exceeds the current age estimate of the universe points toward an early cosmos that was forming stars and structures at a pace the standard timeline cannot comfortably accommodate. One data point carries limited weight on its own, but combined with the impossible galaxies, the supermassive early black holes, and the mismatch in expansion rates, this ancient star contributes to a growing picture of a cosmos that formed faster, denser, and earlier than every model predicts. Something was accelerating processes in the early universe that no identified mechanism can fully explain. And then JWST looked at the invisible scaffolding supposed to hold everything together, and found it arranged differently than the blueprints described. Dark matter is the most studied invisible substance in the history of science. Astronomers cannot see it. No instrument has ever directly detected a dark matter particle. Every attempt to catch one in a laboratory detector has returned empty results. Yet its gravitational influence is woven through the structure of the entire universe, and the evidence for its existence is overwhelming. Galaxies spin faster than they should if only visible matter held them together. Galaxy clusters bend light far more than their visible mass allows. The large-scale structure of the cosmos matches simulations built on dark matter's gravitational influence with striking precision. Lambda CDM makes specific, testable predictions about how dark matter distributes itself. It should cluster most densely at the centers of galaxies, forming halos extending far beyond the visible edges of the stellar disk. In galaxy clusters, it should aggregate into large connected structures, tracing the paths of cosmic filaments. The model predicts densities, distributions, and the way smaller dark matter clumps orbit within larger ones. JWST's gravitational lensing surveys are now testing those predictions at a precision that previous telescopes could not approach. Gravitational lensing is the effect where a massive object curves the path of light from objects behind it. The more mass concentrated in a region, the more it bends and distorts the images of background galaxies. By analyzing those distortions, astronomers can map where mass is located, including invisible mass, without ever needing to detect dark matter directly. The maps emerging from JWST observations partially match, partially contradict, and in several significant cases directly conflict with standard model predictions. The core cusp problem has returned with new intensity. Lambda CDM predicts that dark matter density should peak sharply at the centers of galaxies, a steep, dense distribution called a cusp. Observations across many galaxy types instead show flatter distributions in those central regions, more like smooth cores than sharp cusps. This tension existed before JWST and was subject to various proposed solutions involving the disruptive effects of stellar activity on dark matter distribution. JWST's higher resolution measurements are showing the discrepancy persisting in galaxy types where those solutions should not apply. A separate issue involves the number and mass distribution of satellite galaxies. Lambda CDM predicts that large galaxies should be surrounded by hundreds of small dark matter subhalos, most hosting tiny dwarf galaxies. JWST is finding that the actual population of satellites around several studied galaxies falls short of predictions in ways that earlier surveys had already hinted at, but could not firmly establish. The missing satellites remain missing. Most provocatively, mapping exercises targeting galaxy clusters at intermediate distances have found regions where the lensing signal, the measure of concentrated mass, does not align with the visible matter in the way dark matter models predict. The mass is concentrated in slightly different locations. The discrepancy is small but systematic across multiple observations. Small systematic discrepancies are the kind that broke Newtonian mechanics in the late 1800s. A planet's orbit that deviated slightly from predictions eventually revealed a new planet. When those same slight systematic deviations persisted elsewhere, they eventually revealed relativity. The maps are consistent, and they are not fitting the model. Something even harder to accept was waiting at the very edge of what the maps could measure. The standard model of cosmology sets a scale limit on structure. Gravity works at the speed of its own propagation, bound by the same cosmic speed limit as light. In the time available since the Big Bang, Gravity can only have organized matter across distances that fit within what cosmologists call the particle horizon, the maximum distance over which any causal interaction could have occurred. Within that horizon, structure forms. Beyond it, the universe should be statistically uniform, the same in all directions, with no organized features on scales exceeding certain theoretical limits. JWST is finding structures that exceed those limits. The most prominent example involves a network of galaxy filaments and clusters catalogued as one of the largest known structures in the observable universe. Extended JWST observations, mapping gravitational lensing across a broad region of sky, revealed that this structure, a web of connected galaxy groups spanning an enormous swath of cosmic space, shows coherent organization on scales approaching 1.5 billion light-years. The Standard Model predicts that structures beyond approximately 1.2 billion light-years should show no coherent organization. The universe at those scales should be a statistical average, random, spread evenly, unremarkable. 1.5 billion light-years is not a slight overshoot. Structures of this magnitude had been hinted at by previous surveys. The Sloan Great Wall, discovered in the early 2000s, and the Hercules Corona Borealis Great Wall, identified later, pushed the boundaries of what the Standard Model could accommodate. Each discovery generated fierce debate. Critics proposed that the statistical methods used to define them were unreliable, that what appeared to be a single coherent structure was actually a coincidental alignment of separate systems. JWST's gravitational lensing data addresses some of those criticisms directly. Lensing measures actual mass distribution, not just the positions of visible galaxies. When the mass map matches the galaxy positions, when the invisible and visible components of a large structure agree with each other, the case for genuine large-scale coherence becomes harder to dismiss as an alignment artifact. Several groups reviewing the JWST lensing data have concluded that at least some of the anomalously large structures are genuine, representing real coherent gravitationally connected systems on scales the universe should not have had time to organize. Proposed explanations include the possibility that the universe is older than the standard timeline suggests. Old enough that gravity has had time to produce what is being observed. That would require revising the expansion history and the Hubble constant, connecting directly back to the tension described earlier. Alternatively, the initial conditions immediately after the Big Bang may have seeded specific density patterns that produced large-scale structure faster than standard scenarios predict. A small number of researchers have proposed something more fundamental. That general relativity, the theory of gravity underlying all of these calculations, may behave differently on cosmological scales than at the scales where it has been tested and confirmed. If gravity is modified on the largest scales, the rate at which structure grows could be dramatically different from standard predictions. Modified gravity is not a popular proposal. It carries powerful theoretical objections, but the data pushing toward it is becoming harder to argue away. And everything discussed so far assumed the presence of dark matter. One galaxy was about to suggest that dark matter had never arrived at all. In the story of the universe, dark matter is the skeleton. Without it, galaxies cannot form fast enough. Ordinary matter, the atoms making up stars, planets, and everything visible, does not carry enough gravitational pull to collapse into a galaxy on its own within the available time. Dark matter falls into dense halos first, creating gravitational wells that ordinary matter then falls into. Take away the dark matter, and the galaxies do not assemble. The model is clear on this. So when a galaxy was found with almost none, the field stopped. The galaxy sits roughly 320 million light-years from Earth, designated NGC 1052 DF2. It is an ultra-diffuse galaxy, large in physical extent, but extremely low in surface brightness, with stars spread thinly across a region comparable in size to the Milky Way. Its unusual appearance first attracted attention because it looks like a galaxy that was somehow never finished. The critical measurement came from its kinematics. How fast stars and star clusters move around the galaxy's center reveals how much total mass the galaxy contains, including invisible mass. If dark matter is present in the expected ratio, the stars should orbit faster than if only visible matter holds the system together. The orbital velocities of the star clusters in this galaxy point to a total mass consistent almost entirely with its visible stellar content. The dark matter, if present, is somewhere between a tiny fraction of the expected amount and effectively absent. The initial announcement in 2018 generated fierce debate. Critics identified possible errors in the distance measurement. If the galaxy was closer than estimated, its physical size would be smaller, and the velocity measurements would be reinterpreted. Subsequent observations with multiple independent methods confirmed the distance. The galaxy is where the original estimate placed it. JWST observations have since added detail without resolving the central puzzle. The telescope's sensitivity to faint stellar populations has allowed more precise mass estimates, and those estimates continue to point toward dark matter deficiency in a class of objects that should be dominated by it. Two explanations compete. The first involves tidal stripping. If the galaxy passed close to the much larger nearby galaxy NGC 1052 in the distant past, gravitational forces from that encounter could have torn away much of its dark matter halo, leaving behind mainly the stars. This is physically plausible, and detailed models have been constructed showing how such an interaction could produce something resembling what is observed. The second explanation is more radical. Some theorists argue that dark matter-free galaxies demonstrate that dark matter does not actually exist as a particle substance. Instead, they propose that gravity itself behaves differently at very low accelerations, a theory called modified Newtonian dynamics. Under that framework, a galaxy forming in a specific gravitational environment could naturally lack the signatures of dark matter, without dark matter ever being present. Modified Newtonian dynamics has struggled to account for galaxy cluster observations where dark matter's influence appears undeniable, but it fits certain individual galaxy kinematics better than the standard model does. The universe appears to be playing by different rules in different locations. That is either the sign of incomplete observations, or a deeper truth about what the laws of physics actually are. And stepping back from individual galaxies to the full scale of cosmic architecture, JWST was revealing something that no simulation had predicted: a universe that behaved less like scattered debris and more like something organized from within. Step back far enough from any individual galaxy or cluster, and the universe arranges itself into something that resembles biology. Long thread-like filaments of matter stretch between dense nodes. Vast, nearly empty spaces, called voids, occupy the regions between those threads. The overall pattern, mapped across hundreds of millions of light years, echoes the structure of a neural network more closely than it resembles any random scattering of mass. Cosmologists named it the cosmic web decades ago. They predicted its existence from the physics of gravity acting on slight density variations in the early universe. Computer simulations produced it consistently. Surveys from the early 2000s confirmed the broad architecture. The cosmic web was one of the great predictive successes of modern cosmology. JWST is now revealing its internal structure in detail that transforms the web from a confirmed outline into something dynamic. And what it is showing inside the filaments is raising questions the broad strokes maps never could. The filaments themselves are not uniform threads. JWST's infrared capabilities allow it to detect faint emission from hydrogen gas, tracing the spine of the filaments. Gas existing at temperatures too low for visible light telescopes to capture, but well within JWST's detection range. The resulting maps show filaments that are braided, clumped, and structured at smaller scales than simulations predicted. Concentrations of matter within the filaments appear in locations and at densities that models place slightly off. The fine structure of the Webb does not perfectly match what was expected. Galaxy formation rates differ depending on whether a galaxy is embedded deep within a filament, sitting at a node where filaments intersect, or isolated in a void region. JWST's ability to characterize galaxies at high redshift while simultaneously mapping the larger structure they inhabit is producing the first detailed picture of how environment shapes evolution. Galaxies forming inside filaments appear to consume their gas and stop making new stars faster than galaxies in voids. The dense environment accelerates a galaxy's life cycle. This effect was theoretically predicted, but never directly observed at the distances JWST now accesses. Seeing it operate in the deep cosmic past is confirming the theory, while simultaneously revealing that the effect is stronger than any model calculated. Even more striking are the detections at filament intersections. Where multiple filaments converge, the density of matter spikes and galaxy clusters form. At several of these intersections in the deep JWST images, the rate of galaxy formation happening in real time, visible because the light from those regions shows spectral features associated with active star birth, exceeds predictions for those cosmic epochs by a significant margin. Something drives unusually intense activity at the nodes of the cosmic web at specific moments in cosmic history. Researchers are mapping those moments across multiple redshifts, tracking when the bursts happen and how long they last. The pattern emerging suggests that the cosmic web is dynamic, channeling matter, accelerating and quenching star formation according to a rhythm that no current model fully captures. A universe with a pulse, a structure that acts less like an inanimate distribution of mass and more like a system with internal dynamics working toward an outcome. The deeper JWST looks into the web, the more organized it appears, and in the sections that appear most organized, something was drifting free, untethered from any star, paired with another object just like itself, following no rule anyone had ever written down. A rogue planet is exactly what the name implies, a world with no star, no orbit, no sun rising over its horizon, just a planet drifting through the cold dark between stars, untethered from any system, moving alone through the galaxy at whatever velocity it inherited when something ejected it from its birthplace. Rogue planets were theoretically expected. Every planetary system forms from a disk of gas and dust that almost never produces a perfectly stable configuration on the first attempt. Gravitational interactions between forming planets during the chaotic early phase of a solar system can fling smaller worlds outward with enough velocity to escape entirely. Some of these outcasts drift into interstellar space. The galaxy should be full of them. JWST confirmed they exist in numbers far exceeding previous estimates. That alone was significant. But the discovery generating the most theoretical disruption was not the rogue planets themselves. It was finding them in pairs. In a star-forming region called the Orion Nebula, one of the nearest and most observed stellar nurseries in the galaxy, at roughly 1,300 light-years from Earth, JWST detected dozens of pairs of planet-sized objects drifting freely through the nebula without any parent star. They moved together, separated by distances ranging from several times the Earth-Sun distance to much larger gaps, gravitationally bound to each other and to nothing else. The team that identified them coined an informal name, Jupiter Mass Binary Objects, using the abbreviation JUMBOs because the formal designation was too cumbersome for regular use. The problem is simple and total. Theory does not produce these objects. Planets form around stars from the leftovers of stellar formation. You need a star first, then a disk, then the disk clumps into planets. Ejection from a stellar system produces solitary rogues, not pairs. For two planet-sized objects to be ejected together and remain bound to each other after ejection, the gravitational geometry of the encounter would need to be extraordinarily precise. Far more precise than random stellar interactions allow at the frequency JWST observed. Alternative formation channels have been proposed. Some theorists suggest these paired objects formed independently from unusually small pockets of dense gas in the nebula, collapsing directly into planet-sized bodies, the way stars form but at much smaller scales. This process, called fragmentation, has not been observed at planetary mass scales and is theoretically difficult because gas clouds that small typically cannot sustain the collapse needed to produce a stable object. Others propose that the pairs formed around a star were ejected together through an unusually complex multi-body gravitational interaction and happened to remain bound by sheer coincidence of geometry. The mathematics allows this in principle. The frequency at which JWST found these pairs makes coincidence an uncomfortable explanation. The Orion Nebula detections numbered in the dozens within a single targeted observation campaign. Extrapolated to the full galaxy, the population could be enormous. Hundreds of millions of paired, starless worlds drifting through interstellar space. Nothing in the current model of planetary formation or stellar dynamics generates that population. The objects exist, the explanation does not yet. And in the stellar nursery surrounding these drifting pairs, the stars themselves were forming at a pace that made the unexplained planets seem like the lesser mystery. Every star begins the same way, a cloud of gas and dust, cold and spread thin across light years of space, begins to compress under its own gravity. The compression heats the core. Pressure builds. The process takes millions of years just to reach ignition. Once a star lights up, the radiation it produces pushes outward against the surrounding gas, slowing further collapse and regulating how much additional material falls in. This feedback mechanism puts a ceiling on how fast any star-forming region can produce new stars. JWST is observing star-forming regions that appear to have broken through the ceiling. The telescope's infrared sensitivity allows it to peer through the thick dust clouds that surround stellar nurseries, regions that were completely opaque to visible light instruments. What those clouds had hidden was the actual rate of stellar birth happening inside them. And in several cases, the activity levels far exceed what the feedback regulation model predicts. In a region called the Cosmic Cliffs, part of the Carina Nebula, JWST's first images revealed hundreds of previously unseen young stellar objects embedded in dense gas columns. The sheer number of forming stars in a region whose surface area and gas density had already been measured implied a star formation rate higher than any model applying standard feedback physics predicted for that location. More striking were detections in a series of starburst galaxies, observed at high redshift, galaxies in the early universe, undergoing episodes of intensely elevated star production. JWST's spectroscopic data for several of these galaxies showed star formation rates exceeding several hundred times the rate of our own Milky Way, which produces roughly one new star per year. Some exceeded 1,000 solar masses of new stars forming every single year. Even starburst galaxies were expected, as they are a known phenomenon. But the starbursts JWST is identifying in the early universe are occurring at redshifts, meaning at distances and times where the gas reservoirs available to fuel such formation rates should not be large enough to sustain them for the durations the observations imply. The inference is that either the gas is being replenished faster than it is consumed, requiring continuous inflow from the surrounding cosmic web at extraordinary rates, or the efficiency with which gas converts into stars in these environments far exceeds standard values. Current theoretical models set the fraction of available gas that converts into stars at a few percent at most. The conditions producing the observed star formation rates in some early JWST targets require efficiencies several times higher. Some analyses point toward efficiencies approaching or exceeding 50%, fractions that no physical mechanism in the standard framework generates. Proposals exist. Dense gas in the early universe had different properties than modern molecular clouds. The interstellar medium in the first billion years was likely more turbulent, warmer, and structured differently. Some simulations incorporating those differences produce higher efficiencies. Whether they produce efficiencies high enough to match the observations remains an active area of modeling. The stars forming at these extraordinary rates did not all survive gently. Some of their most direct legacies were not new suns, but dying worlds. And JWST managed to photograph one of those deaths in real time. Planetary science has always operated at the extreme limit of patience. Most processes shaping planets unfold over millions or billions of years. The formation of a mountain range, the erosion of a canyon, the loss of an atmosphere. These happen on timescales that make human lifespans irrelevant. No scientist has ever expected to watch a planet change in any meaningful way during their career, let alone during a single observing campaign. JWST produced the first direct observation of a planet losing its atmosphere in real time. The planet is called AU Microscopii b, orbiting a young active red dwarf star approximately 32 light-years from Earth. It was discovered before JWST and is classified as a Neptune-sized world, sitting extremely close to its host star. Its orbital period is less than 9 days, placing it in the category of planets exposed to intense stellar radiation and strong gravitational forces continuously. What JWST detected was an asymmetric transit signature when the planet crossed the face of its star. The signal on the side trailing behind in its orbit differed from the signal on the leading side in a way that indicated a comet-like tail of gas streaming away from the atmosphere. Material was leaving the planet and being pushed away by stellar wind and radiation pressure, creating a detectable outflow that extended beyond the planet's gravitational grip. The measurement itself is not a surprise in the broadest sense. Atmospheric escape from close-in planets is predicted by models and had been inferred from population-level statistics, where a gap exists in the size distribution of exoplanets, suggesting that smaller close-in planets have been stripped down to bare rocky cores by this exact process. But observing it directly, watching a specific world shedding its atmosphere in real time during targeted observations, crossed a threshold from inference into documented fact. What JWST showed was the mechanism in action: high-energy radiation from the host star ionizing the upper atmosphere, heating it beyond the temperature at which the planet's gravity can retain it, and the resulting outflow accelerating away in a structured stream rather than diffusing uniformly. The rate of atmospheric loss measured from the transit data implies a timeline. At the observed escape rate, the planet's remaining volatile envelope will be largely gone within several 100 million years. Compared to the age of the solar system, that is a relatively short sentence. The finding carries a direct implication for planetary habitability surveys. When JWST characterizes the atmosphere of a candidate habitable world, the observation is a snapshot. Whether that atmosphere existed 500 million years ago and whether it will persist 500 million years from now depends on the same stellar activity levels and orbital configurations JWST can also measure. The telescope is not just cataloging what exists, it is revealing which worlds are in the process of becoming something different, and at what speed. Some of those worlds, at distances far beyond the reach of any follow-up mission, were revealing their hidden companions in an entirely unexpected way. The solar system runs like a clock. All 8 planets orbit the Sun in the same direction, counterclockwise when viewed from above the Sun's north pole. Their orbits are nearly flat, confined to a relatively thin plane called the ecliptic. This arrangement is not coincidental. It reflects the physics of formation, every planet condensed from the same rotating disk of gas, inheriting the disk's angular momentum and therefore moving in the same direction at roughly the same inclination. JWST is finding planetary systems where this rule has been overturned. The evidence arrives through dust rings. Young planetary systems frequently contain rings of dust and debris, the leftover material from formation settling into stable orbits. JWST's infrared sensitivity allows it to resolve the fine structure of these rings at distances where no previous instrument could. In several observed systems, the dust ring geometry does not align with what the system's geometry predicts. The rings appear tilted, warped or structured in ways that require a gravitational perturber pulling material out of the disk plane. Detailed modeling of those warped geometries points to the most likely explanation: a planet orbiting at a steep inclination relative to the main disk, in some cases nearly perpendicular to the primary plane, and in others moving in retrograde, orbiting in the opposite direction to everything else in the system. Retrograde orbits are known in extreme cases. A small number of exoplanets discovered through transit methods have been confirmed as retrograde, typically massive hot Jupiters, whose orbits were presumably tilted through gravitational interactions with other bodies early in the system's history. These are exceptional objects. What JWST's dust ring surveys are suggesting goes further. In several young stellar systems, the warping patterns indicate retrograde bodies are present at locations and sizes where they represent a significant component of the system's architecture. Not an outlier, but a structural feature. The mechanism proposed most often is a phenomenon called Kozai-Lidov cycling, in which a distant companion star gravitationally torques the orbit of an inner planet over long timescales, gradually tilting it until it flips to retrograde. This mechanism is well understood in theory and has been confirmed in specific cases, but the frequency of the warp signatures in JWST's Young Systems survey is higher than Kozai-Lidov alone can explain for the stellar environments involved. Several of the systems showing the strongest warp signatures lack any detected companion star that could be driving the effect. Something is flipping planetary orbits in systems where the known mechanisms cannot account for it. A hidden companion too faint for JWST to detect directly. A relic of formation dynamics not yet captured in any simulation. Or a gravitational influence from an object the model of planet formation has not yet accounted for. Meanwhile, at the scale of entire galaxy clusters, JWST was capturing something so enormous and violent, it reordered the intuition of what the word catastrophic even means. A galaxy is enormous. The Milky Way spans roughly 100,000 light-years from edge to edge and contains several 100 billion stars. A large galaxy cluster contains hundreds to thousands of individual galaxies. When two of those clusters collide, the event produces the largest energetic phenomena in the observable universe, releasing more energy in the collision shockwave than all the stars in both clusters emit over billions of years. JWST has produced the sharpest observations ever made of an active cluster collision, and the data is rewriting what researchers thought they understood about the physics of these events. The collision under study involves two galaxy clusters merging at a combined velocity of several million miles per hour. The galaxies themselves, small compared to the vast spaces between them, mostly pass through each other without direct stellar collisions. The real violence occurs in the hot plasma that fills the space between galaxies inside each cluster. This plasma, called the intracluster medium, represents the majority of the cluster's ordinary matter. When two clusters collide, this plasma does interact, generating shock waves and turbulence on scales that dwarf individual galaxies. JWST's contributions came from combining its infrared galaxy mapping with X-ray data from other observatories to build a composite picture of the collision zone. In that picture, shockwaves expanding outward from the collision site were traced across a region stretching over 6 million light-years, more than 60 times the diameter of the Milky Way. Inside the shockwave front, galaxies are being compressed and disrupted. Star formation is being triggered along the shockwave boundary as compressed gas in those galaxies crosses the threshold for collapse. JWST detected multiple galaxies within the collision zone, showing signs of simultaneous star formation bursts, events directly triggered by the mechanical energy of the merger shockwave passing through them. The dark matter behavior in the collision zone matched predictions in broad outline and deviated in specific details. Dark matter halos from both clusters are passing through each other in the same way they do in the famous bullet cluster, remaining concentrated around their galaxies rather than mixing. This is considered strong evidence for the particle nature of dark matter, since a modification of gravity explanation struggles to reproduce it. But the precise shape of the dark matter distribution, as the halos overlap, showed asymmetries that theoretical models did not predict. What drew the most attention was the scale of the shockwave itself, 6 million light-years. The standard models of cluster collision physics cap the detectable shockwave extent at distances somewhat below that range. Generating a coherent shockwave that maintains structural integrity at 6 million light-years requires either more total energy in the collision than the visible mass accounts for, or a medium through which the wave propagates that is more uniform and less turbulent than the intracluster medium was expected to be. The cluster is carrying more energy than it should, and that energy has to come from somewhere. Far from the fire of colliding clusters, in the cooling aftermath of stellar death, JWST found something that blurred the line between cosmic destruction and the origins of life itself. When a massive star ends its life in a supernova, the explosion tears the star apart in seconds. The outer layers are blasted into space at a fraction of the speed of light. The shock wave sweeps through the surrounding interstellar medium, heating gas to temperatures of millions of degrees. At those temperatures, complex molecules should not survive. The energy levels involved shred chemical bonds without difficulty. JWST found complex organic molecules flourishing in the aftermath anyway. The observations targeted a supernova remnant, the expanding shell of material thrown outward by a stellar explosion. Previous instruments had detected simple molecules in these environments: water, carbon monoxide, silicon oxide, the building blocks. Expected, JWST's spectrographs reached deeper and found something unexpected: polycyclic aromatic hydrocarbons, abbreviated as PAHs, are ring-shaped carbon molecules representing the beginning of genuine chemical complexity. They form the structural backbone of more intricate organic chemistry. On Earth, they appear in coal, oil, and the output of combustion. In biology, related ring structures form the core of DNA bases and many essential proteins. Finding them concentrated in a supernova remnant rewrites the story of where organic chemistry begins. The prevailing model placed complex molecule formation primarily in cold, dense molecular clouds, regions of space far from energetic events, where low temperatures allow chemistry to proceed slowly without constant disruption. Hot, turbulent supernova remnants were considered hostile environments for this chemistry. What JWST showed was that the shock wave from the explosion is not simply destroying molecules. In certain regions within the remnant, the shockwave compression and subsequent cooling is actively manufacturing them. Material destroyed in the explosion is recombining as the remnant expands and cools, and some of that recombination is producing molecular structures more complex than what existed before the star exploded. A star dying, and in the process of dying, seeding the surrounding space with the chemical precursors of life. The implication reaches far beyond a single remnant. Supernovae are not rare events. The Milky Way produces roughly 1 to 2 per century. Every supernova expels several solar masses of material, If each remnant functions as a factory for complex organics during its expansion and cooling phase, then the interstellar medium is continuously being enriched with the molecular components from which planetary chemistry can eventually build biology. Scientists already knew that supernovae produce the heavy elements that rocky planets and living organisms require: carbon, oxygen, nitrogen, iron. The entire periodic table beyond hydrogen and helium was forged in stellar interiors and scattered by stellar deaths. JWST adds another layer. The explosions may also initiate the first steps of the chemical complexity that defines life, before any planet even forms to host it. Stars die, and in dying, they appear to set the table. What JWST captured next challenged the timeline of that table setting in a way that made the supernova chemistry seem almost orderly by comparison. Every model of galaxy formation makes a fundamental prediction about the order in which things happen. Stars form in the center first. The central region of a galaxy is where gas density is highest, where the first collapse occurs, where the first stellar generations live and die. The outer regions, the disk, and the extended halo fill in later. Old stars should concentrate at the center. New stars should form in the disk where fresh gas has arrived. JWST is found in galaxies where the order is reversed. In a selection of early universe galaxies examined by multiple research groups, the age distribution of stellar populations runs counter to everything galaxy formation models predict. The stars at the outer edges of these galaxies are old, ancient stellar populations, metal-poor and evolved, occupying the fringes of the galaxy, while the core blazes with ongoing star formation involving young, bright, chemically enriched stars. The central regions of these galaxies are the youngest parts of the system. Several explanations have been proposed, none entirely satisfying. One involves what cosmologists call inside-out quenching, followed by reignition. In this scenario, the galaxy initially formed stars throughout its structure in a more standard pattern. Then star formation was suppressed in the outer regions first, perhaps by feedback from an active central black hole heating and expelling gas. At a later stage, fresh gas inflows reignited star formation, specifically in the central region, creating the appearance of a galaxy that formed backwards, when in reality the sequence involves multiple distinct phases. This explanation works on paper. Making it work in practice requires a precise sequence of events, with specific timing at specific locations within the galaxy. For one or two objects, coincidence could arrange that sequence. For the population of reversed gradient galaxies JWST has identified, coincidence becomes statistically implausible. A second explanation challenges the initial conditions. If the outer regions of these galaxies were seeded with stellar material very early, perhaps through the merger of smaller pre-existing galaxies or through a brief burst of formation triggered by an external event, and if those stars then evolved and quieted while fresh gas accumulated toward the center through subsequent inflow, a backwards age gradient could develop more naturally. The difficulty here is that merging enough pre-existing old stellar populations into the outer regions of a galaxy without disrupting the galaxy's structure. A third possibility, discussed quietly and without consensus, is that our understanding of how angular momentum distributes gas within forming galaxies is now resolving. If gas behaves differently in the early universe than models predict, routing toward the center more efficiently than expected, while leaving the outer regions to form from earlier, different material. The backwards profile could emerge from formation physics rather than exceptional evolutionary history. The backwards galaxies may be telling us something about inflow, about angular momentum, about how the raw material of star formation moves through a young galaxy. Or they may be telling us that the standard picture of how any galaxy builds itself, inside out and center first, needs to be rewritten. And as JWST pulled back to the largest canvas, It found a region of the universe so empty that the emptiness itself had become a standing question with no accepted answer. In the late 1970s, astronomers mapping the distribution of galaxies stumbled onto something that should not have been there. A region of space roughly 330 million light-years across, occupying a volume so vast that 60 full-sized copies of the Milky Way galaxy could fit side by side across its diameter. Inside this region, almost nothing. A handful of galaxies where thousands should have been. A hole in the universe. The Boötes void has been studied and debated since its discovery. The Standard Model allows for voids as a natural feature of the cosmic web. Matter evacuates from low-density regions, drawn toward the filaments and walls of the web, creating underdense bubbles as a natural consequence of gravitational dynamics. Some voids are expected, reasonable ones. The Boötes void is not reasonable by those standards. Its diameter exceeds what cosmological simulations consistently produce through standard gravitational dynamics in the available cosmic time. Getting matter to evacuate that completely from a region that large requires either more time than has passed or an unusually powerful mechanism. JWST has added new data to the conversation. Pointed observations targeting the boundary regions of the void, where the transition from mere emptiness to the surrounding galaxy filaments occurs, have revealed that the transition is sharper than expected. Standard void formation predicts a gradual density gradient at the edges, a soft fade from underdense interior to typical density exterior. The Boötes void shows an unusually steep boundary. Matter drops off sharply rather than gradually. Sharp boundaries imply a mechanism. A uniform gravitational evacuation over billions of years would produce a smooth edge, something that empties a region quickly, or something that prevents matter from re-entering a boundary once it forms, produces a sharp one. Several proposals have been raised. A concentration of dark energy within the void region exerting stronger outward pressure than the surrounding cosmos, effectively pushing matter away from the interior at an elevated rate. A relic signature from the very early universe where a particularly low-density region of the primordial distribution evolved into a void that exceeds normal scaling. An artifact of a large-scale flow not captured in the simulation frameworks used to generate comparison models. None of these explanations is universally accepted. The sharpness of the void boundary is a relatively new measurement from JWST data and has not yet been confirmed by independent analysis with full statistical rigor. What is confirmed? The Boötes void is larger than standard models comfortably allow, emptier than gravity alone easily explains, and its edge is structured in a way that points toward a specific cause rather than passive gravitational drainage. The new observations have made a decades-old mystery sharper rather than softer. Empty as the void is, the strangest signals coming from JWST were not arriving from empty space. They were arriving on a schedule. Astronomy is full of repeating signals. Pulsars rotating neutron stars emit beams of radio energy like cosmic lighthouses, sweeping past Earth with clockwork precision. Binary star systems pulse in brightness as one star eclipses the other. Variable stars expand and contract on regular cycles. Repetition in astrophysics usually has a mechanical explanation rooted in rotation, orbital geometry, or stellar physics. Fast radio bursts are different. These events last milliseconds. A burst of radio energy arrives, intense enough to briefly outshine everything else in the sky at those wavelengths, and then it is gone. The first was identified in archival data from 2007 and caused immediate debate about whether it was even real. Within a decade, dozens had been catalogued. Within 2 decades, thousands. Most occur once and never repeat. Some repeat. A subset of fast radio bursts has now been observed, producing multiple events from the same source. And within that subset, a smaller group has shown something that moves the phenomenon from intriguing to genuinely difficult to explain. Periodicity, repeating on a schedule, active for a predictable window of time, then quiet for a predictable interval, then active again. JWST's contribution lies in the follow-up. After radio observatories detect a burst and establish a source location, JWST can be pointed at that region to examine the environment the burst originates from. The infrared observations help identify the host galaxy, its distance, its type, and the local conditions around the source. Several repeating burst sources have now been localized to specific regions within their host galaxies. The environments vary. Some are located near active star-forming regions. Others are in older stellar populations. The diversity of environments makes a single common source mechanism less likely. The most constrained explanation for repeating bursts with periodicity involves a magnetar, an extraordinarily dense neutron star with a magnetic field trillions of times stronger than Earth's, orbiting within a binary system, or processing in a way that periodically aims its emission toward us. Magnetars are confirmed astrophysical objects. A known magnetar in our own galaxy produced a fast radio burst in 2020, confirming the connection at least for some events. But magnetar precession models struggle to reproduce the specific periodicity values observed in the most well-characterized repeaters. The periods range from days to hundreds of days. Magnetar precession at those timescales requires physical parameters that sit at the edge of what standard neutron star models allow. Alternative explanations include orbital geometry of a compact object system, where the burst source is periodically blocked or focused by a companion object, or a geometric model where the emitting region sweeps through our line of sight as the source rotates on a very long period. Every explanation is physically grounded. None has been confirmed, and the periodic signals keep arriving on schedule, indifferent to the debate about what generates them. In the most extreme corners of the exoplanet data, JWST had moved from detecting molecular signals to something almost cinematic, the actual weather of alien worlds. Weather is not exceptional. Every planet in our solar system has it in some form. Mars has dust storms covering the entire planet for months. Jupiter's Great Red Spot is a storm larger than Earth, but has persisted for centuries. Venus has winds that circle the entire planet in 4 days while the surface barely rotates. Weather is what happens when an atmosphere exists and energy drives it. JWST has produced the first detailed weather maps of planets orbiting other stars. The technique builds on the same transmission spectroscopy used to detect atmospheric molecules, but applies it at multiple orbital phases rather than just during transit. By observing a planet as it moves through its full orbit and measuring how the thermal emission from its atmosphere changes with viewing angle, astronomers can reconstruct the temperature distribution across the planet's surface and detect large-scale atmospheric features. JWST applied this to a hot Jupiter and produced a temperature map showing a hotspot offset from the point directly facing the host star. The hotspot, the location of peak atmospheric temperature, was shifted eastward in the direction of atmospheric circulation by strong equatorial winds. The offset itself is not surprising. It had been predicted and previously inferred through less direct methods. The resolution JWST achieved in mapping it was entirely new. Within that temperature map, the data contained structure at smaller scales. Irregularities in the thermal pattern suggesting convective cells, rising columns of hot gas and descending columns of cooler gas, operating on scales of thousands of miles. Continent-sized storm systems built from the same physics as Earth's weather, but operating at temperatures exceeding 2,000 degrees Fahrenheit, over a world where no surface exists beneath the clouds. For planets in the habitable zone, weather carries a different significance. Whether a world capable of hosting liquid water actually does host it depends partly on atmospheric dynamics. A planet with the right temperature on average might be too hot across most of its surface and too cold everywhere else if its atmospheric circulation distributes heat inefficiently. A planet with a dynamic, distributing atmosphere could maintain habitable conditions across a far larger surface area. JWST's weather mapping capability means that habitability assessments for specific exoplanets can now include atmospheric dynamics, not just average temperature and chemical composition. A planet scoring well on all static measures of habitability, but showing atmospheric patterns indicating runaway feedback or extreme temperature gradients, can be assessed more honestly than before. 2 exoplanets in the habitable zones of their respective host stars have received weather mapping observations as of the most recent observation cycles. The results from those specific worlds are still being processed at the time these words were written. The implications of what that processing reveals could be significant. And before any of those results arrived, JWST's instruments captured something else entirely. Something that was not explained by any of the standard categories of known astrophysics and did not resolve into any known source. Science runs on anomalies. The measurements that do not fit are the ones that eventually force new frameworks. An unexplained deviation in Mercury's orbital precession led to general relativity. An unexpected dimming of distant supernovae revealed dark energy. The history of physics is a history of the unexplained eventually breaking open into something transformative. In 2023, JWST's instruments recorded a series of infrared readings from a targeted region of sky that did not match any known astrophysical source. The observations targeted a dense region of the early universe as part of a survey program. The data returned a diffuse infrared signal distributed across the observation field with a spectral shape that did not correspond to any catalogued object type. It was not galaxy emission, which has a characteristic spectral profile. It was not stellar continuum radiation. It did not match the signature of hot dust, cold dust, ionized gas, or any known component of the interstellar or intergalactic medium. The team running the analysis exhausted the standard checklist. Instrument artifacts were tested by rotating the telescope and repeating the observation from a different position angle. The signal persisted and did not rotate with the instrument, ruling out any fixed detector artifact. Stray light contamination from bright objects outside the field of view was modeled and subtracted. The residual signal held. Data reduction pipeline errors were investigated by multiple independent groups, applying different software to the same raw data. The signal was reproducible. Published results describing the anomaly appeared in preprint form before full peer review and generated immediate attention. The authors were careful throughout to present the finding as an unexplained signal rather than a detection of anything specific, and they explicitly invited the astrophysical community to propose explanations. Several proposals came. The most straightforward involved populations of galaxies or other astrophysical objects at specific redshifts whose emission lines happen to produce a combined spectrum mimicking the observed signal when blended together at the sensitivity level JWST reaches. Testing this requires deeper spectroscopic follow-up observations to attempt to resolve the signal into individual components. A second class of explanations pointed toward decay signatures from dark matter candidates. Certain theoretical dark matter particles are predicted to decay over cosmic timescales, emitting photons in specific wavelength ranges. The spatial distribution and spectral shape of some dark matter decay models have been compared against the anomalous signal. The match is not perfect, but is not obviously incompatible. A third group of proposals, received more cautiously by the community, suggested the signal could represent a genuinely new astrophysical component of the universe, one not yet included in any model, possibly connected to the excess backgrounds seen in previous, less sensitive surveys that had been set aside as unexplained. No consensus has formed, follow-up observations have been scheduled, but results were pending as of the writing of this script. The anomalous signal may resolve into something familiar with more data. Science requires that possibility to be fully tested before anything else is concluded, but it may not resolve into anything familiar at all. And from the unexplained signal, JWST's data was quietly beginning to touch questions that physics had long reserved for philosophy. The multiverse is the kind of idea that makes careful scientists uncomfortable. It lives at the edge of testability, which is the edge of what science can legitimately claim to address. The standard formulation goes like this: if the laws of physics allow for regions of space beyond our observable horizon to have different physical constants, different strengths of gravity, different values for the cosmological constant, then our universe may be one of an enormous number of separate universes, each with its own set of rules. The most scientifically grounded version of this idea emerges from inflationary cosmology, the same framework that explains the extraordinary uniformity of the early universe. Inflation theory predicts that the brief exponential expansion immediately after the Big Bang may not have stopped uniformly everywhere. In some regions it continues, eternally producing new expanding bubbles, each a universe, each potentially different. This was theoretical structure, without observational contact. Then JWST began returning data that some physicists are treating as indirect, tentative, and hotly contested contact. The anomalies in the cosmic microwave background that earlier telescopes detected, specific cold and hot spots, alignment patterns, and what researchers named the axis of evil because its presence violated the statistical isotropy the standard model demands, have now been examined in conjunction with JWST's deep galaxy maps. When the positions of the anomalies are mapped against the large-scale structure that JWST has resolved in the deep universe, certain correlations appear. Regions where the cosmic microwave background shows statistically significant deviations from the expected uniform pattern correspond to regions where the large-scale distribution of matter also shows deviations from what simulations predict. This correlation was not expected if the anomalies are random statistical fluctuations. Random fluctuations in one dataset should not correlate with structure in a completely different dataset. A team of cosmologists published an analysis in late 2023, arguing that this correlation is more consistent with a collision between our universe and a neighboring bubble universe in the inflationary multiverse than with any known internal mechanism. In their model, a collision during the early inflationary epoch would have created a large-scale coherent imprint on both the matter distribution and the background radiation, precisely because both were established during the same brief window. The response from the broader community ranged from intrigued to skeptical to dismissive, depending on the physicist's position on both the multiverse question and the statistical significance of the correlations. Several independent groups argued that the apparent correlation could arise from known large-scale structure effects not fully accounted for in the comparison models. The authors acknowledged those objections while maintaining that their proposed explanation was the most parsimonious fit to the combined dataset. Testable predictions exist. If the bubble collision hypothesis is correct, additional JWST observations of specific sky regions should reveal large-scale matter distribution patterns consistent with the model's predictions. Several of those regions are now in the telescope's observing queue. Science is approaching the multiverse, slowly, carefully, and with no guarantee of arrival, but approaching. And approaching alongside it, from a completely different direction, was the possibility that the origin story of the universe itself was missing its first chapter. The Big Bang is not an explosion in space, it is an expansion of space itself, the beginning of space, the beginning of time, the beginning of everything physics can describe. Asking what came before it is, by the standard framework, a category error. Time did not exist before the Big Bang. There is no before. JWST is generating data that some cosmologists believe can only be fully explained by something that existed before the beginning. The case builds across multiple observations, the structures too large to have formed in the available time. The galaxies fully assembled far too early. The clustering patterns in the ancient universe that resemble acoustic echoes in a medium with a prior history. The anomalies in the cosmic microwave background that appear to correlate with large-scale matter distribution in ways that an entirely fresh start at the Big Bang should not produce. Taken individually, each of these can be argued around. Taken as a pattern, they are generating a serious scientific conversation about what the standard initial conditions of the universe are missing. Bouncing cosmology is the most developed theoretical framework for a universe with a prehistory. In this model, a prior universe contracted under its own gravity, approached a state of extreme density, and then re-expanded. Quantum gravity effects, operating at the scale where general relativity and quantum mechanics intersect, would have prevented a true singularity and instead produced a bounce. The new expanding phase from the inside would look exactly like our Big Bang. The prior universe would not be destroyed in this bounce. Its large-scale structure, its density fluctuations, its matter distribution would be compressed and then re-expanded, imprinting themselves on the new universe's initial conditions. The acoustic patterns, the structural seeds, the anomalies in the background radiation, all of these could reflect the geometry of the universe that preceded ours. A second framework involves loop quantum cosmology, a specific approach to quantizing gravity that also predicts a bounce rather than a true beginning. In that model, the universe before the Big Bang was itself expanding, contracting, or in some dynamic state, and the bounce represents not a unique creation event, but a transition point in a potentially endless cycle. What makes these frameworks more than speculative philosophy in light of JWST is the existence of observational predictions. Bouncing cosmology predicts specific features in the power spectrum of primordial gravitational waves, ripples in space-time from the earliest moments of the universe. Those gravitational wave signals, if they exist, carry information about the pre-bounce state. JWST does not detect gravitational waves, but the telescope's data on primordial structure informs which pre-bounce initial conditions are consistent with what we observe. Constraining the problem from the output end is the first step towards testing the input. The field is not claiming a pre-existing universe is confirmed. It is claiming the data is no longer fully consistent with a universe that simply appeared from nothing. Something may have come first, and the evidence for it is accumulating in the same instrument designed to see light from the first stars. A pattern was forming across every chapter of this story, and some researchers had begun to name it. At some point, an accumulation of anomalies stops being a list of independent problems and starts being a message. The early galaxies too massive to exist, the black holes too large for their age, the expansion rate that does not match the origin story, the structures too big for the available time, the dark matter maps that deviate from predictions, the galaxy with no dark matter, the star older than the universe, the cosmic microwave background anomalies, correlated with large-scale structure, the little red dots with no explanation, the rogue planet pairs with no formation mechanism. Every one of these could be argued as an isolated anomaly awaiting a specific solution. Scientists are obligated to treat them that way because the methodology of science demands that each claim be tested on its own merits before being woven into a broader narrative. Combining anomalies prematurely, forcing them into a unified story before each is individually confirmed, is how science goes wrong. But the pattern has not gone unnoticed by careful researchers. A subset of cosmologists has begun publishing papers that step back from individual anomalies and ask what category of explanation could, in principle, address all of them simultaneously. This is not the same as claiming to have found that explanation. It is the prior step, mapping the shape of the missing piece, before trying to name it. The common thread running through most of the major JWST anomalies is time. The universe appears to have formed structure faster than the standard model allows. At every scale examined, galaxies formed faster, black holes grew faster, clusters assembled faster. If a single modification to the standard model could accelerate structure formation across all scales in the early universe, it would resolve a remarkable number of separate anomalies at once. Early dark energy, mentioned in the context of the Hubble tension, is one candidate. A brief additional energy component in the first fraction of a second after the Big Bang could have altered expansion rates, density contrasts, and structure formation timescales simultaneously. It carries observational signatures that future experiments are specifically designed to hunt. Modified gravity is a second candidate. If gravity behaves even slightly differently at the cosmic scales involved in large structure formation, the cascade of effects through galaxy formation, black hole growth, and cosmic web organization could produce something resembling what JWST observes. A non-standard initial condition potentially seeded by a pre-existing universe, as discussed in the previous chapter, is a third candidate. If the Big Bang began with more structure already present than a simple inflationary model produces, every downstream process would have more to build on, and more time effectively to build it. None of these is confirmed. All are being actively tested. The scientific community has not coalesced around any single explanation, but the direction of the conversation has shifted noticeably. JWST has moved the field from a state of confidence in its framework to a state of genuinely open questioning. That transition, in any science, is the moment just before something breaks open entirely. Everything the telescope has found points toward a revision. The only remaining question is how large that revision will need to be. Science revisions sound abstract. They live in journals. They get discussed in conference rooms and seminar halls. The average person goes about their life while the framework of the universe gets quietly dismantled and rebuilt. It is easy to feel disconnected from the process. But every time physics has fundamentally revised its framework, the material consequences eventually arrived at a scale that changed how humans live. Newton's mechanics enabled the Industrial Revolution and every machine that followed. Maxwell's equations describing electromagnetism were considered pure mathematics until they became electric power and radio communication. Einstein's relativity seemed impossibly remote from daily life until it became the correction factor that makes GPS satellites accurate to within feet rather than miles, meaning every navigation system in every phone on Earth runs on a relativistic calculation every second. Quantum mechanics was the most abstract and philosophically disorienting revision in the history of science. It was also the foundation of every semiconductor, every transistor, every computer, and every digital device ever built. What would rewriting cosmology produce? The immediate answer involves the most fundamental unsolved problems in energy and materials science. Dark matter, if it is confirmed to be a particle, represents a substance that fills the universe at a density roughly 5 times that of all ordinary matter. If its properties were understood at the particle level, interacting with it would become a theoretical possibility rather than a fantasy. Dark matter's gravitational behavior, if it follows rules that can be characterized, opens engineering questions that currently have no framework even to be asked. Dark energy, the component driving the universe's accelerating expansion and representing roughly 70% of the total energy content of the cosmos, is currently described by a single number with no mechanistic understanding behind it. If JWST's anomalies eventually force a revised understanding of dark energy, of what it is and how it operates, The question of whether it can be influenced or utilized becomes, at minimum, a physically serious one. Understanding what produced the Big Bang or what existed before it is not merely philosophical. The conditions in the first fraction of the first second after the Big Bang forged the laws of physics that everything since has followed. Understanding those conditions in detail means understanding why the laws of physics are what they are, rather than something slightly different. That understanding could reveal whether the constants of physics are genuinely fixed, or whether they represent one configuration among possible alternatives that could, under specific conditions, be accessed. These are not near-term engineering proposals. They are the territory that opens when the map gets redrawn. Every impossibility JWST has recorded is a location where the current map ends. Beyond those edges, in the space where the anomalies live, are the answers to questions humanity has not yet learned to ask with enough precision to expect an answer. The telescope did not arrive with answers. It arrived with a better map of the questions. And one of those questions was never written into its mission objectives at all. JWST was designed to see the first light of the universe, to observe the formation of the earliest stars and galaxies, to characterize the atmospheres of exoplanets, to study the life cycle of stars and the physics of our own solar system in new detail. Every mirror segment, every detector array, every spectroscopic instrument was optimized for those goals. The question it was never designed to answer is the oldest one humanity has ever asked. Are we alone? That question belonged to radio telescopes sweeping for artificial signals. It belonged to future missions with biosignature detectors built specifically for the task. It belonged to a generation of telescopes not yet designed, funding proposals not yet written, technologies not yet developed. Answering it was always something for the future, always something further along the road. JWST opened the road and found it shorter than anyone expected. The dimethyl sulfide signal from K2. 18b, tentative as it remains, is the first time in human history that a specific molecule associated with life has appeared in the atmosphere of a planet orbiting in the habitable zone of another star. The instrument was not optimized for that detection. It was not pointed at that planet as part of a biosignature hunting program. The signal appeared in the course of standard atmospheric characterization, the same kind of observation the telescope was actually designed to perform. The first possible sign of life beyond Earth arrived as a side effect, and JWST is only at the beginning of its operational life. The telescope was designed to function for 20 years. The first 2 years produced every anomaly described in this journey, every impossible galaxy, every paradoxical timeline, every deviation from the expected map. If the first 2 years rewrote the questions, 20 years may rewrite the answers. By the end of this decade, JWST will have examined hundreds of habitable zone planets through transmission spectroscopy. If the dimethyl sulfide signal on K2, 18b, is confirmed, it becomes the first point in a statistical sample. A second confirmed biosignature on a second world would shift the question from possibility to probability with a force that no cautious scientific language could contain. A negative result across hundreds of worlds would sharpen what we know about the rarity of life's chemical signatures in the universe, which is its own extraordinary information. The impossible galaxies, if they hold under continued scrutiny, will eventually demand a revised cosmological model. That revision will likely resolve some current anomalies and reveal new ones, because that is always how it works. The timeline of the universe, the nature of dark matter and dark energy, the question of what existed before the Big Bang, all of these are now observational questions, rather than philosophical ones. JWST made them testable, but beneath all of it, at the base of every impossible discovery, every anomalous reading, every broken prediction, the deepest question remains. unchanged. We built a telescope to see the beginning of everything, and it looked back at us with a universe far stranger, far older, far more structured, and far more alive in possibility than the model we built to describe it. The impossible thing JWST may have detected is not any single galaxy, signal, or anomaly. The impossible thing is a universe that consistently, stubbornly refuses to be as simple as the best minds in history built it to be. Whatever is out there, it has not finished surprising us, and JWST has barely begun to